Hi, everyone. My name is Michael Sanders. I'm working in the research lab of Professor Chi Wong from the Aerospace Department at San Diego State University. And this is my 5-minute Blitz presentation for the ACSESS event entitled A Big Data Enhanced Nonlinear Decomposition Method for Minimal Channel Flow Turbulence. Turbulence is a highly nonlinear and chaotic phenomena with a large degree of freedom, as I'm sure many of you know. For an example of this turbulent behavior, you can see this image just below me. Estimating the evolution of flow states for a turbulent flow is a challenging task, and it's even more challenging if you try to do it in backwards time. Professor Wong conducts research on adjoint methods for turbulent flows, and he was seeking a method to find the intrinsic coordinates of a turbulent flow field. So essentially, we're looking for a lower dimensional representation of this complex flow field. To that end, we developed a neural network-based autoencoder, which summarizes the equilibrium distribution of turbulence into a low-dimensional embedding. So you can think of this as a compression algorithm that it compresses the data in the flow field to 1/16th the size. The data that we used to train the neural network was generated using the Johns Hopkins code LESCO. So let's talk about the structure of this neural network. The neural network is an autoencoder, which means that the loss function is trying to match the output to the input. So after a series of transformations, we are trying to generate an output that matches the same input that went in. But during these series of transformations, the dimension of the data is reduced. So we reduce the dimension of the data using parallel paths of convolution and average pooling operations until we reach a desired latent space. And then we decompress the data using a series of convolution transposes and upsampling. So you can see in the schematic below, we have several paths of different kernel sizes that try to detect features on a different scale. For instance, we may have a 3x3x3 kernel, which will detect features on a 3x3x3 scale, and we might have a 7x7x7 that will detect larger features in the flow. And as I mentioned, this is an autoencoder, so the training loss is trying to match the output to the input. And if we're able to match the output to the input, we can be reasonably certain that the latent space is capturing some lower dimensional representation of the field. So let's take a look at how the network performs. The network was trained over 15,000 epochs. And this is the training data set just to show that the network is potentially able to learn our data set. These are slices of 3D data fields. So we're sending in three-dimensional flow fields, but we're just checking two-dimensional slices to see if we're able to capture the structures. So these colorful contour plots are U, V, and W velocity data. The plot on the top represents the original field, and the plot on the bottom represents the reconstructed field after it has gone through the autoencoder. At a minimum, these contour plots pass the eye test of being representative of the velocity field, and I've also computed the mean squared error of each of these, so we can see that the error in the training data is of order 0.1. We've also plotted the Q criterion below my head here. The Q criterion is a visualization technique which displays the turbulent structures in the flow field. And again, on top is the original Q criterion structures for the original dataset, and the bottom is the Q criterion structures that are preserved after going through the autoencoder transformation. And again, you can see that the general features of the structure are preserved. But this is a bit of an unfair test because this is data that the neural network was used to train on. So we expect if the network is able to learn, it will represent this data well because it saw it many times during training. So now let's look at how it performs with data that it has never seen before. Here is test data, and once again, you can see that the match is fairly good. The overall error is of the same order of approximately order 0.1, and the Q criterion plots show once again that the general turbulent structures are preserved. In the future, we're hoping to leverage this autoencoder by incorporating it into an adjoint code, which pertains more directly to the research of Professor Wong. Professor Wong's research is on adjoint methods for estimating turbulent flow fields in backwards time. However, as with many computational fluid dynamics problems, the computational cost and the complexity increases dramatically as the sizes of your matrices increase. And so we're hoping to use this autoencoder to keep the overall dimension of the problem small to help solve larger and more complex problems in the future. We are also hopeful that the autoencoder will capture only the most important features of the flow, and as such can help us find the best signal in noisy data. Once again, my name is Michael Sanders, and if you'd like to learn more about my research, please come to my poster. Thank you very much for your attention. I hope you enjoy the ACSESS event.